Le Chatelier's principle states that an equilibrium system that is subjected to any stressor will tend to shift to a new equilibrium state in attempting to offset that stressor. In previous lessons, we talked about Le Chatelier's principle with regard to concentration of substances, addition of catalysts, changes in pressure or volume of gaseous systems, and this last lesson on Le Chatelier's principle is going to deal with changes in temperature, that is, energy changes in an equilibrium system. Changes in temperature always result in shifts in the equilibrium position and changes in the value of the equilibrium constant. Let's start with an exothermic reaction. We have reactants on the left, products on the right, and for an exothermic reaction, perhaps you remember that heat is released. In other words, energy exits the system. Delta H is the change in enthalpy, but we can think of it as heat. Heat exits the system. So if we wanted to put heat into this equation, we would put it on the right side. In other words, when this reaction proceeds, we produce some heat. Now, we simply treat temperature or heat as another reaction component. And earlier, we talked about how if you increase the amount of a substance, the equilibrium will shift away from that. If you decrease the amount of a substance, the equilibrium will shift towards that. It's the same idea here. As the temperature increases, we can think of the system saying, wow, look at all this heat I have. I've got to use it up. Which way do you have to shift? You have to shift to the left to use that up. And if you shift to the left, clearly the amount of product decreases and the amount of reactant increases. Well, since K is products divided by reactants, if the product amount has decreased and the reactant amount has increased, the value of K, the numerical value of K, will decrease. Similarly, as the temperature decreases, we can think of it as we're taking heat out, taking heat out, taking heat out, and the system says, better make more, shift right. And when we shift right, the amount of products gets bigger, the amount of reactants drops, and since K is products divided by reactants, the value of K will increase. Similarly, for an endothermic reaction, where the enthalpy is positive, that is, we are putting heat into the system in order to make it go. In other words, heat goes on the reactant side. As we increase the temperature, look at the equation. The system says, wow, look at all this extra heat I got to get rid of it. Shift right. And when you shift right, you get more product and less, so the value of K will increase. As the temperature in this system decreases, again, look at the equation. Taking heat out as the temperature decreases, taking heat out, better make more, shift left, and when we shift left, the amount of product decreases, the amount of reactant increases, the value of K is going to drop. So don't memorize these ideas. You need to think and understand them. Now, is this related to transition lenses? And the answer is yes. In transition lenses, there's an equilibrium system going on between AgCl, which is more or less colorless or clear, especially very tiny particles of it, and you can see on the product side neutral silver and neutral chlorine molecules. Energy is on the reactant side, that is, this is an endothermic process. And when we're inside, this system is at equilibrium. When we go outside, sunlight is more intense than inside light, so the energy term increases. We're suddenly pumping more energy into the system. The system says, ooh, too much energy, got to get rid of it. Shift to the right. and when you shift to the right, the glasses darken. They reach a new equilibrium state when you're outside in the sunlight. Then you go inside. When we go inside, the energy term decreases because inside light is less intense than sunlight. When the energy term decreases, the system says, hey, what happened to all my energy? I better make more. Shift to the left, and when you shift to the left, the glasses lighten up again. Let's summarize Le Chatelier's principle by predicting the shifts for these proposed changes in this reaction. I should add that these lettered choices, A, B, C, and D, we're doing each one of these separately. So we're not doing A and then in addition adding B to that and then in addition adding C. We're doing one and we're predicting the shift. Then what if we did the next one? What would the shift be? Letter A, if we add Cl2, again I'm looking at the reaction equation, if we put more Cl2 in, the system is going to say, whoa, too much Cl2, better get rid of it, shift to the left. In a separate case, if we look at the reaction and we're going to remove PCl3, take some PCl3 out, take more out, take more out. Pretty soon the system notices and says, hey, where's my PCl3? I better make more. Shift right. Suppose instead we were to increase the pressure. This is a gaseous system, so pressure volume changes might apply with regard to shifting. We can see that on the reactant side we have 1 mole of gas. On the product side we have 1 mole plus another 1 mole, so that's 2 moles. And whenever we increase the pressure of a gaseous system, the gaseous system wants to get smaller. So which way would we shift to produce less volume? And that would be to the left. What about increasing the temperature? We're told in the upper right corner here that the delta H is 87.9 kilojoules. If we wanted to rewrite that into the equation itself, the positive sign of the delta H means that we have an endothermic reaction. The energy term would appear on the reactant side. And now we can see that if we increase the energy, increase this, increase the energy, increase the energy, the system is going to say, man, got too much energy. I better get rid of some of that, use it up, shift right.